Hi, Alma.
Okay.
Thank you very much for joining. Myself, Naveen Kumar, and I'm European Project Manager for Irish Bioeconomy Foundation. And we are working with a Horizon Europe Rural Bio project, which supports rural communities in adopting sustainable bio-based solutions. And this project aimed to create regional hubs to promote knowledge exchange, training, and market access for bio-based product. It aimed to strengthen rural economic resilience and environment sustainability by fostering cultural and circular bioeconomy practices. Salma, thank you very much for joining and contributing to the technological information. I would let you introduce and have the floor, and you can start on with your slides after your introduction. And I am going to turn off my camera. Thank you very much, Salma.
Problem, and thank you, Naveen, for the invitation to come and talk to you and your members today. So my name is Dr. Alma
Thank you.
Siggins. I'm a lecturer and a Royal Society Research Ireland University Research Fellow here in the University of Galway. And I've worked on biochar quite a bit. I'm going to talk a little bit today about some of the research projects that we've been running, but also the wider context of what's been happening with biochar research. So if you just bear with me, and I will share these. No, actually, apologies now. I don't think that will share like that. So let me just stop sharing and start the slideshow first, because that will work better. Okay. Now, so thank you very much. So I'm going to talk to you a little bit today about some novel biochar applications. Okay, so just to start off with a little bit of an explanation as to what biochar is. So biochar is a high carbon-based material that we use for a wide range of applications, both in industry but also in research. So we start off with an input material, which is an organic biomass, so a carbon-based compound. And there's a wide range of input materials that we can use for production of biochar. From a sustainable point of view, we like to use materials that would be considered to be waste products. So things such as wood chips from forestry, waste material from agriculture, which can include manure, excuse me, but also other industry waste. So things like olive pits or coconut husks. So anything that has a high carbon content and is a waste material. So we'll dry that material and then we'll grind it to a fairly uniform size, depending on what we're looking for. And then we put that material through our pyrolysis reactor. So the pyrolysis reactor is going to heat that material to quite a high temperature, typically 600 to 800 degrees Celsius, in the absence of oxygen. And after that process, which can usually take about 30 minutes or so at that chosen temperature, we get an output, which is a solid, which is our biochar, a gas, which is our biogas, and a liquid bio oil. And we also can heat and energy production. So the biochar that we're producing is going to look a little bit like this. It looks somewhat like the charcoal that you might use in a barbecue. And the kind of size and the structure of the biochar is going to be very dependent on the feedstock that you used as your input material. So typically, to be considered true biochar, it has to have a hydrogen to organic carbon ratio of greater than 0.7. And there are different classes of biochar that are dependent on the organic carbon content of the product. If we look at this under a microscope, we can see that it has actually a really interesting surface structure. And if we zoom in, for example, on this piece here, this is a scanning electron microscope image that we took here at the university. And at this resolution, we can see that it has quite a complex structure, and all these pores and channels and complicated structure gives it a very high surface area. So our BET surface area will allow us to classify our biochars as a low, moderate, or high surface area. And those surface areas can be over 500 meters squared per gram, which can be very high. Based on that surface area typically, but sometimes also on things like the surface functional groups of the biochar, we can characterize its appropriateness for different applications. So soil amendment is the most commonly utilized and known, but there's also a lot of research in construction material and batteries, which I'll talk about. For medium surface area, we're looking at plant growth and composting, water treatment, and high surface area for remediation and carbon capture, where we're primarily focusing on adsorption processes and also anaerobic digestion. So biochar was really first used as a soil amendment. And when I say first used, we know that there are terra preta soils in the Amazon basin that date back 2,500 years. So these were soils that have a high clay content, and you can see, I'm just going to get my laser pointer. You can see here these clay soils without any biochar amendment. And then this is a similar type of soil to which biochar has been extensively added. The extent of the terra preta soils indicate that this wasn't just occasional campfires, that this was actually done intentionally. And we do know that adding biochar to soil is going to cause increased fertility. And we can see this here where we have a crop growing on these clay soils with low plant growth, and then much better plant growth growing on the amended soils. So we know that with soil application, we get increased organic matter and also macronutrients. We see because of that then increased plant growth. We can also have a liming effect. So biochar tends to have quite a high pH, and it's an excellent way to absorb contaminants, but it also allows for attachment of microbes, which can be a very positive thing. And it's something that we're working on quite a bit in Galway. So just to go through some of the non-soil applications, biochar is used extensively in batteries, and lithium-ion batteries are of particular interest. There's a growing use of technologies that use lithium-ion batteries, and especially with electric vehicles coming more and more on site. So currently we use a graphite anode, but graphite is a very non-renewable product, and it requires really high temperatures, can be over 3,000 degrees Celsius to produce graphite. So this has a high environmental impact, but there's a high demand because for lithium-ion batteries, we need 10 to 15 times the amount of lithium as we do graphite. So we need 10 to 15 times more graphite than lithium. And just to give you an idea, when we're looking at the efficiency of these batteries in terms of the reversible capacity, graphite has a reversible capacity of 200 to 300 milliamp hours per gram. Our untreated biochar, so just taken and pyrolyzed directly from things like bamboo, cotton stalk, or aquatic plants, have been reported in literature to have a similar reversible capacity. But if we look at doped or activated biochar, so where we are going to activate it after the biochar is produced, we can get an even higher reversible capacity. So there's a lot of potential to use this biochar for batteries. There's a lot of research at the minute in the use of biochar for construction, and particularly within concrete. So we can use biochar to replace the aggregates. And we have seen in research that this increases flexural strength by 26%, and it can reduce the bulk density because biochar is quite a light, low density material. There have been a number of studies that have also looked at the use of biochar in cement, where it decreases thermal conductivity, so it improves the insulation qualities of this cement. Resin composites, which is associated with improved elongation, and also in plastic composites, which gives a greater tensile and flexural strength. So adsorption is more of an area that I have worked with directly in our research, and biochar has a huge capacity for adsorption of both organic and inorganic compounds. So with organic, it can be associated with pore filling. So as we saw in the scanning electron microscope picture, we have all these pores and channels within the biochar that can capture these different contaminants directly within the pores. Or we have different functional groups on the surface of the biochar that can cause a chemical reaction with our contaminant and capture it on the surface of the biochar. With metals as well, we can have these chemical reactions, or the biochar can trigger a change in the form of the metal to allow it to precipitate, where it can be extracted and purified more easily. So one project that we were working on was looking at the organic contaminant trichloroethylene, which is an organic solvent. And here on the left in this graph, you can see we were looking at a range of different biochars alongside granular activated carbon, which is kind of the gold standard for adsorption assays. But what we found was that there was a number of biochars, one of our spruce biochars and an oak biochar, that actually performed better than granular activated carbon and removing TC from liquid. And then we progressed and we further this experiment in a column system where we were pumping the wastewater up through a column that was packed with biochar. And on an ongoing basis, we got over 99% removal, but he also got the establishment of a microbial community that had the capacity to degrade the TCE. And this led on to our current project, which is looking at absorption of methane. And what we found in our current project is that this biochar has the capacity to absorb about 130 milligrams of methane per gram of biochar. So we know that methane is a very potent and important greenhouse gas. So the ability to absorb it and prevent that being released into the atmosphere is really important. When we had dry conditions, so just methane being directly exposed to the biochar, we got absorption occurring in about 15 minutes or less. When we had an aqueous system, so we had a vial with liquid and biochar in that liquid and then methane in the headspace, we still got absorption, but it took over 240 hours. So we're really interested in this because the fundamental concept of the project is to look at not just the methane absorption, but then its utilization by a group of bacteria that have the capacity to oxidize methane. So they're called methanotrophs. And what we've been able to show, and this brings us back to the concept of using biochar as a microbial carrier, this is another one of our SEM images, and you can see all these pores and channels in the biochar. But we've been able to get some of our methanotrophic bacteria to colonize the biochar. So here you can see a cluster that are growing inside a pore. So the idea being that the microorganisms are going to form a biofilm on the biochar, and then they'll be able to utilize the methane that's absorbed from the system. And what we found is that at very low concentrations of biochar, we are seeing increased growth. So this is showing the difference in the amount of microbes that are growing compared to a control vial with no biochar. So the control has been normalized to 0. Where we get a positive value, we're showing increased growth, and where we get a negative value, we're showing decreased growth. So at low concentrations, the microbes like this biochar quite a lot. But we do see that as the biochar concentration increases, we get a significant decrease in growth. So that's a very short, brief introduction to some of the projects we've been working on and some of the wider field around potential applications for biochar use. Biochar has a huge potential. The range of applications that it's been used for are only growing. There's a lot of interest around industry and research at developing novel applications and processes for using biochar. It's a very low cost material. It's a very circular economy approach, particularly by using waste materials for biochar production, and it makes a contribution to multiple sustainable development goals. And I think this interest in biochar is really reflected. If you look at the graph on the right-hand side, this is the number of journal publications per year that feature the word biochar. And you can see a huge increase and a continuing increase in interest in biochar research. So that's everything for me. Thank you very much. I will pass back to Naveen.
Thank you, Alma. It was really great webinar, like especially like coming, I was just feeling the nostalgia when I was working with the different kinds of biochar. So it was very informative, and I think like people will be helpful to understand. So thank you for joining and our initiative and contributing to the technological information. IBF and Rural Bio team is very thankful to you for your contribution.
No problem.